All right, welcome back. Next, what I'd like to do is quickly run through some real-world use cases for trees. These aren't just theoretical things. This isn't just about, interview prep. Trees are used all the time. Even if you're not fully conscious of it, you've interacted with trees both as a JavaScript developer most likely, but then also just as a user of the internet. So the most common example is HTML and the DOM, the Document Object Model. So when we think about HTML, it lends itself to a tree-like structure, right? We have elements, and inside of elements, we can have nested elements that are children. And we can keep having children nested and nested and nested further down. And it's a parent-child relationship between those HTML elements, which are just text. But then once it gets to the browser, after a request, we get the response. The browser then reads through it all, parses it, and it creates the DOM, the Document Object Model. And in Chrome, we get this nice debugger. We can click through, sort of an interactive way of viewing the different nodes. But behind the scenes, there is a corresponding JavaScript object for each one of these nodes. So there's a body. We can access it just by typing document.body. And it prints text for us here, but it's actually an object. And if we do dot, we can see it has a bunch of properties, a bunch of methods we can call. And we can do things like look at its children. And it gives us a list of children. So let's take the first thing in there. That gives us a node, and we can do .children on that. And is it just one thing in there? Yeah, it looks like there's just one child div inside of that first child. Anyway, if you're not familiar with the DOM, I wouldn't worry about it. Just know that it's a tree structure, very, very commonly used one. So another application has to do with network routing. Definitely not my expertise. I'm not even going to try and explain how it works, but if you go to the routing page in Wikipedia, we get all sorts of diagrams of trees over here. So these are different delivery schemes for how basically a message is transmitted to a node or to multiple nodes. And you can see that we've got some tree structures going on here. And that's pretty much all I'll say about that because I know nothing about network routing. But behind the scenes, there are some trees being used. There's a bunch of classic computer science logic that goes into finding the shortest path. Anyways, next up, we'll talk about abstract syntax trees. So these are a way of describing the syntax of a programming language using a tree structure. So without going into too much detail, it really doesn't matter. Honestly, all that matters is that you see that this is a tree structure. Whatever language this is for, it's from Wikipedia if you do want to read more about it. We have, let's say, a while loop. Inside of a while block, we have a condition as part of the while. And then we also have the body inside of that while. And in that condition, we can have a comparison between a variable and a constant. And this is a very succinct, shortened version. It's missing a lot of logic. But the point is to show you that this is a way of, basically, if you were writing code to take in other code and run that code or to parse that code or to make sure it's valid syntax, you could use an abstract syntax tree to help you out. Next, trees are used in artificial intelligence all the time. There are tons of applications for trees in artificial intelligence and machine learning. Probably the simplest example is something called a Minimax tree. So let's say we're building a tic-tac-toe game. We want to build an AI that is very good, that isn't just picking random moves. We could basically break down the logic of the game into a tree. And we basically would say, here's a given state of the board, and these are all the possible moves that the human player could make. They are O, the computer is X. And what we see here is, okay, if the human player plays an O here, the best possible move to make is to put an X right here. And in that way, X would win. If an O goes here, the best possible move is to put an X in the middle. And then it depends what O does next. There's multiple options. Basically, this tree structure just describes a bunch of different possible options for what could happen. And after a given move by the opponent, the best possible next move. So that's a really superficial, we didn't even scratch the surface of how you actually implement this and what the minimax part is of the logic. But all that I want to show you is that this is basically called a decision tree. You have different decisions that you make, branching points, and you follow one, and then that splits, and you follow the next decision, and you keep going. And these have applications in very complicated classification algorithms, for example, not just tic-tac-toe AI. And then finally, probably the simplest example is the way that your folders are modeled in an operating system. If you see something like this on a Mac or a PC, your computer is represented as a tree structure. There's all these directories, It's hierarchical. There's a root. There is a topmost folder. On a Mac, I actually don't know what it is anymore. On your account, it's the root directory, but there's multiple accounts you can have on a computer. Anyways, it doesn't matter. But let's just say we're looking at a given folder. This folder inside, this is maybe our root. We have 2 other folders inside, and then they have files. And yeah, technically, this has like 2 types of nodes. You could say there's files and folders. But the structure itself is tree-like. We have all these branches, and those children have children of their own, and so on. So that's just a quick introduction to some of the real-world use cases for trees. I assure you, though, this is not purely theoretical thing. It's not just an exercise. This is stuff that comes up all the time in programming. One example I totally forgot to mention is JSON. So if you've ever worked with JSON, JavaScript Object Notation, you're getting, an AJAX call, you're sending in a request, and you're getting some data from an API. When you parse that response from a string into JavaScript, or if you're using Python or whatever language you're using, there's code that is traversing a tree or creating a tree-like structure. As we can see here, I'm using a Chrome extension just to view some child nodes, and they each have children, and this is a tree structure. You could represent this easily. Well, I shouldn't say easily. It suits itself to being represented by a tree. It's a lot of work, but it still is a tree structure where we have parents and child nodes, but there's, at the end of the day, a single root. All right, I'll leave it off there. There's a lot of different uses for trees.